Okay, so I have reevaluated, I've gotten the questions reevaluated by metal people, and you must have gotten the uh, answer papers. Have you received them by now?
Yes, sir.
Okay, did you get the satisfactory, I mean, as much as possible, the satisfactory evaluation, or were your marks changed where you were expecting it to change?
Yes, sir.
Okay, good. If you have any problem still that, with your evaluation, I would request you not to send me an email, but discuss it with your TAs on Thursday session, and that uh, uh, those people will take corrective action. I think most of the doubts and queries would have been solved, but if still there is any query which is left, then you can contact your TAs on Thursday. Please don't send me an email for the correction of the mark purpose. Okay, so I hope most of you have got your marks corrected. Okay, and now second thing, we are going to start with, let me, fine. Now, I have somebody asked me a question. I think it was Tarang Soni regarding the idea of abstraction. Is Tarang Soni online?
Sir.
Okay, Tarang, can you repeat your question? It was regarding abstraction, right? What is exactly the meaning of various levels of abstraction in computer architecture?
Yes, sir. It was regarding that.
Okay. So the idea of abstraction. So let me just. So let me do this. The idea of abstraction is to give details only as much as you need. So for example, take example of your laptop. Now, if a business person or your parents or a young person who wants to use laptop, and if he asks you that, what is in a laptop, then, the highest level of abstraction would be, all you have to do is turn on the power button. Then, you will see, say, the Chrome icon inside. You click on that Chrome icon, it will open up. Then you type gmail.com and, you can check your mail, or, you can type the website which you want to see, and you will be able to see the website. So that is purpose of most of the senior people or very young people, who are just interested in checking their mail or visiting websites. So that is the highest level of abstraction. They don't know what is inside the laptop. They don't know what operating system is. All they know is I need to turn on the power button and click on these icons. So that is the highest level of abstraction. Then as you go lower down, then the idea of operating system would come in. Then if you are a programmer, then your abstraction would be slightly a lower level of abstraction, which would say what kind of compiler is there. If you are, say, hardware software co-designer, then you would also like to know what kind of processor is there, what kind of instruction set architecture is there, along with all the other things which I mentioned for top two layers. So the level of abstraction is, and then, if you want to go to very, very deep level, the deepest level of abstraction, or in other words, no abstraction, would be to talk about anything from the point of view of physics. So physics, when it comes down to, you talk about atomic layer and, what happens to each atom and what reaction is done. And that is like, the most bottom thing. So that is no abstraction. It is all physics. So beyond that, when you go to transistor level, you go to gate level. So you're going up in abstraction level. So abstraction is, you are teaching someone something, which is up to a certain, like, here also we are doing an abstraction. We are opening up a processor. We are talking about processor, but, we said that we'll talk only about data path. We will not talk about control path. Yes, of course, it is required. It is there. But to learn about the basics of computer architecture, you don't need to know the control circuitry. You just assume it is there. So just like, in driving a car, you don't have to know how your engine works, or, what is the compression ratio of all the cylinders. But, you just say that, okay, it is something is there, it is working what it is supposed to do. So does that answer your question, Taran?
Yes, sir. Yes.
Okay. So, okay, can I move on, Taran?
So, sir, abstraction just means they hiding means hiding the details. Hiding the details. That is it.
Yeah, so abstraction does not always mean hiding the detail. It depends on what level of abstraction you are. So you can hide the details for, like, the highest level of abstraction. You just say, okay, click this button and something will come up, and, you just do it. So that is the highest level of abstraction. And then it is like onion that, you start peeling the layers, and, you go down and more details would start coming out. So depending on what is your interest and what is your education level, based on that, there is abstraction levels are there.
Yes, sir. Sir, because I was asking this because it has been emphasized a lot.
Your voice is not very clear. I can barely hear you.
Now,
Either fault.
now can you hear me?
It is still garbled. Maybe you can keep mic slightly away from your mouth.
Now am I audible, sir?
Well, I mean, slightly better. Go ahead. I mean, I will try to figure out what you are saying. Go ahead.
Sir, I had this question because it has been emphasized a lot in the first chapter, and I could not understand why it is so much important.
So you are saying question was why abstraction is so much important?
Yes, sir, because I could not get why it has been emphasized so much in the first chapter of the.
Okay. If I can understand your question correctly, you are asking that why the abstraction is so much important to understand this. Well,
Yes.
because I can start teaching computer architecture from the point of view of transistors, MOSFET. But, you have not studied MOSFET. So, their first question is, how does MOSFET work? And, but for your purpose, all you need to do is, I mean, you don't need to know how things work. You just assume that it works. So your level of abstraction is beyond the gate level. And, you are talking at the instruction set architecture level. So if I don't provide abstraction, then, you may not understand, that, okay, talking about transistors and gates and how they work may not be sufficient for you to know the subject. And then, you will be going off in a different direction. So it is better to go top down that, okay, this level. So now that I know up to this level. I can go one level below where the level of abstraction is lower. And so then, go all the way down, depending on what's your interest. And then, so it is important to have abstraction to understand the subject. Because,
Yes.
you start learning everything from first principle, then, it is very difficult to understand it.
Yes, sir. Now I got the I,
Okay, okay, good. Now, let us start off with where we left off yesterday. So we were talking about instruction level parallelism, and the idea was how to get our CPI below 1. So as opposed to what you guys are getting, you are always trying to get your CPI above a certain number. In computer architecture, it is exactly opposite. Getting a CPI 1 or below is desirable. So then, you say that, let us do the first problem which we saw was, suppose you're doing this. So you're trying to do something like this. This is your program, a small bit of your program. Now, as you see here, there is a raw hazard between load and add, right? Which is immediately following it. So now, you would say that, okay, you need to have a bubble. So even in a simple 5-stage pipeline, this is going to cause you problem. But, we learned that you can lift some of the instruction which is below it and, execute it before this. You can take this and put it over here. At that time, when I discussed this, I did not explicitly say that, you are doing out of order execution, but, that is what actually I meant. So one way of speeding this program up, forget about, you just have says 5-stage pipeline, no parallel execution paths. Even then, so there is only one execution unit, no parallel multiple execution unit. Then also you can get some advantage if you do scheduling. So that is known as scheduling. And one way of doing is static scheduling. So your compiler is looking at this and telling you that I can do this from some memory location, and then you do and the next cycle do this. So this is static scheduling, which is done by compiler. Now we talk about dynamic scheduling. Now this is, when we talk about dynamic scheduling, we also say that, now this is just a very old way of doing things, having just one execution path. I can have, because, suppose there were instructions, this instruction was somewhere in the middle, and this one was stuck because there is a cache miss. So then, the rest of the program, would be kind of bothered. So if I had like, 2 units, one was like load store, and the other one was, say, just 2-issue thing, and the second one is your normal ALU. Then, while this was stuck over here, I could have sent this in parallel, and then, I could have gotten the execution done. So I could have, that is also called hiding the latency, right? You know that, when your cache is throwing a miss at you, that, okay, whatever data you were trying to load, was not found in data cache. So, let me waste 10 cycles, go down to L2 cache, get it and put it into your R2 register. Now, if you want to hide it, what you would do, you would schedule some instructions, which are not directly dependent on this one. There is no dependence, true dependence on this instruction, and you can start executing them through here. Well, having said that, that only certain type of instruction can go, no other load store can go because, this load store pipeline is occupied. But this pipeline, things can go. And, as long as it is not causing any raw hazard, you can allow it to go. So that's where the dynamic scheduling would. Okay, Megat, please turn off your mic. Now, if you are coming here for dynamic scheduling, then you say, okay, what is dynamic scheduling doing? Now, dynamic scheduling, we assume that usually it is the hardware which is doing. So then you say, what's wrong with compiler doing this? Okay, suppose here you are putting in the value of another register which is yet to be evaluated. Now, static scheduler or compiler, when it opens up, it doesn't know what exactly value would that be. And whether you are putting a variable, so are you going to have a problem or not, would not be known. That problem will be known only once that thing is being evaluated, and then only you can figure out whether it is done or not. So static scheduler has a limitation, or compiler has a limitation. It won't be able to tell you that it is having a problem, or it is going to have a problem, whether these two instructions will have a hazard or not have a hazard. It wouldn't know. So in that case, dynamic scheduling is preferred, where hardware is figuring it out. So what do? So as we discussed, you start bringing 2, 3, 4, depending on how much is what your bandwidth is, those many instructions together. And then you allow your hardware to decide which instruction can go in. So that brings us to this picture. It brings us to this issue stage. And in this issue stage, your hardware would decide whether these instructions can go in or cannot go in, or will have to wait, or whatever. So the advantage of dynamic scheduling as opposed to static scheduling is that first of all, it knows the result, that so that whatever instructions you are bringing in, it would know exactly where it is going or where the register values are coming from. And secondly, see, compiler is very much architecture dependent. So if you change the architecture, then compiler will have to recompile, or you have to write a new compiler. So that makes your compiled program a very, very platform dependent, that I can work only on Cortex A9 processor. But suppose if I give you Cortex A76 or Cortex A55, then you say, okay, I need to write a new compiler for Cortex A55 or Cortex A76. So the better thing is you give most of the responsibility to hardware. So hardware has to figure out. So Cortex A76 would have its own issue stage, or Cortex A55 would have its own issue stage, and that would decide, basically, it would know exactly how many pipeline stages are there or how many parallel pipelines are there. So for that particular case, dynamic scheduling is always preferred, because you don't have, most of the worries which previously for static scheduling was with the compiler, now it is given over to hardware. And hardware designer knows that what changes they were made in hardware. So they would figure out. So it is taking up the problem from software and giving it to the hardware. So that is dynamic scheduling. Does anyone have any question up to understanding of dynamic scheduling? Okay, moving on. Now, we said that, issue stage is one stage, which is like a clerk. So issue stage would decide whether I want to send this instruction to this stage, whether instruction can go, or whether a couple of instructions can go in parallel. Do they have any raw hazard or true dependence? So issue stage has to do two things. Number one is check for compatibility of instruction with the functional units. So these are three functional units. This is functional unit number one, functional unit number two, and functional unit number three. So it would get an instruction package. Now instruction package would be like, since it makes sense that you have three functional units, so you should get at least three instructions together. It is better if you bring in 4 instructions or 5 instructions together, so that issue stage would have some chance of looking for appropriate instructions, because 3 functional units, and if I bring in just 3 instructions, then the chances are very less that all 3 functional units would be filled and instructions would be of right type and no dependence between them. It's very kind of impossible. So what you need to do is you are going to have this issue stage, and just suppose you are sending it 4 instructions and you are giving an assignment. Out of these 4 instructions, find 3 instructions or as many instructions as you can, which first can match with the type of FU, that is functional unit. And number 2, make sure that none of the instructions which goes in parallel have any kind of raw hazard between them. Right? So that is what the issue stage would do. So then, we kind of agreed that, yeah, this is a good thing. And, this is not necessarily just 3 functional pipelines. You can have more if you like. You can have 2 of this and, maybe 2 of this and maybe 2 of Mac. So you can have 6 functional units. So if it is a 6 functional units, then, it would be, you will call it as a 6 issue pipeline. If there are only 2 functional units, so you had only this and this, then it would be a 2 issue. So at the most you can issue 2 instructions together. That's about it. So it's a 2 issue processor. That means it has got 2 functional units, and maximum 2 instructions can be issued at the same time. If I got 3 pipelines, it would be a 3 issue machine. So that means maximum 3 instructions can go in together. But remember, I keep on saying the word maximum. It doesn't mean every time 3 instructions will go. Sometimes only 1 instruction would be able to go. Sometimes 2 instructions would be able to go, right? And sometimes, very rarely 3 instructions would be able to go together. Okay, so we have already talked about this. Now, there is one word which you hear. I mean, I will give you a reading assignment if you're interested in understanding this subject thoroughly. So your reading assignment, it is not compulsory, but if you want to understand this in great detail, then in computer organization and design, in this book, you read from page 342 to 351. This is partial 1, topic 4.1. And in computer architecture, a quantitative approach. In this one, you read 3.4 and 3.5. So that would be page 191 to 208. And they have explained things in much greater detail. If you think you can handle it, you should definitely read it. If you're interested in subject, you must read it. Okay. So now the first thing is we have taken care of, first of all, we are doing out of order execution. So that, starts blinking kind of warning lights to you. But, what about war and wow hazard? So this is what we are going to do. And for that, we are going to study Tomasulo organization or Tomasulo algorithm. Now, as I said, that issue stage is the one which decides, or, which is a bookkeeper. So how will it do bookkeeping? The simpler algorithm which was used before was scoreboarding. The idea was almost same as Tomasulo algorithm, but it is quite basic, so I have not taught it because Tomasulo algorithm is a superset of scoreboarding. So I'm just going directly to scoreboarding. So in scoreboarding, we have to worry about two things. So Robert Tomasulo was working in IBM, and he found out this nice way of figuring out whether there is a problem or not. So he said something like this, and this we have already discussed, but let me go over this again. So if you have, say, 3 functional units, and this functional unit might be ALU type, load store type, MAC type, or some other type. I mean, it could be of any type. So there are 3 functional units. Instructions, let's say this is ALU type, your simple ALU type. This is your MAC type, and this is your load store type. Okay, so instruction which is of ALU type will go here, instruction which are of MAC type will go here, instruction which are load store type will go here. Now, for that, you make a nice reservation station attached to each. It may happen that instruction has come here. 2 instructions had come in the issue stage. One instruction could go into ALU, but second instruction couldn't go into ALU because there are 2 instructions. So one instruction would be sitting down here. Same thing with MAC and same thing with load store. Now, now that you have put it over here, you are given this 5 identifiers for each instruction. The first one is operation. So, whether it's an ALU operation or a MAC operation or a load store operation, so that you will put that. Now, you have got 4 entries, VJ, VK, QJ, and QK. Now, VJ and VK, if those things are directly available from register files, then, you would put that entry into VJ and VK. Like, here we have said add R1, R2, R3. And then, previous instruction could be, say, load R2 from some memory location. And this load is already into this pipeline, and add R1, R2, R3 could not go into ALU pipeline because, it had problem with load. So you made it wait over here in the reservation station. And, you would fill out its program over here. That operation, you would say, okay, it is add operation. VJ R2 is not available from register file. Why it is not available from register file? Because the value is going to change with the instruction which is before that. So you don't put an entry at VJ. R3 is ready. And let us assume that no previous instruction is going to produce R3, or they were there, they finished their execution, and R3's, the latest value of R3 is already written into register file. So in VK, you will put R3. In QJ, you will put functional unit 3. Why? Because this value is coming from functional unit 3. So the entry is there in QJ, and QK there is no entry because R3 is already available. So in the long and short of it, you will put things under VJ and VK only if the value are there in the register file and fresh values are there in the register file. And you will put something under QJ and QK only if that value is still to be computed and it is waiting in one of the functional units. So you can't have entry both in VJ and QJ. So either you have entry in VJ or you have an entry in QJ. Same thing. Either you have entry in VK or entry in QK. You can't have entry in both. If you have entry in both, that means you are wrong somewhere. Is this concept clear?
Sir, yeah, what was QK?
Okay, QK is the same thing. Suppose R3 was not available, means the fresh value of R3 was not available. Say R3 was being calculated in functional unit number 2. Then you will not put R3 under VK, but you will put FU2 under QK.
Okay, sir, thank you.
Yeah. So it depends on where the value is available. Is it available in the register file? If it is available in the register file, then first operand and second operand would be like VJ and VK. If the fresh value is not available in register file, if they are old values, then you say, okay, where is it coming from? Function unit 2 or function unit 3. And this would also take care of, this is called register renaming. That here I did not put R2 over here. I put it as functional unit number 3, some different name to that register. Why? And so, basically there is a register over here, but I'm fictitiously calling it FU3. You can call it T or P or whatever you want to call it. So here what would happen is that I have renamed register R2 as FU3. And because of that, the value till it is calculated, you are not going to look for R2. You are going to look for FU3. And this instruction will always say the value FU3, whether it is coming or not. And whenever it comes, it would use that. If I had put R2 over here and not put our FU3 in the QJ thing, then it would have used the wrong one because it would have then started looking at the register file. The difference in scoreboarding is that scoreboarding will make things wait. That, it did not have any entry of QJ or QK. All it was doing was that, VJ value is not available till it is fully calculated. Only when it is updated into register file and, there's a message coming from register file that R2 is updated, only then, you would put R2 over here. So what it means, it was little wasteful, that it will wait till the value is written into register. So you can compare this with our very simple data forwarding concept that, output of ALU is directly given as an input of ALU for the instruction which is immediately following it and depending on the previous instruction. So here's the same is the case that, you are not waiting for things to be written into register file and then, writing the value of R2. Here, you are saying, okay, within this parallel FU units, you start giving the required data to each other. And so that, you can start calculating, right? Is this concept clear? So this, I have called it as something as register renaming. So R2 is named as FU3. So this thing will not allow to go through till the FU3 value is updated from functional unit 3. And this would take care of your war hazards, that it will not allow you to go and execute this. And you can have there are other examples which are given in the book. If you're interested, you can go and check with it. So now let us, as promised, look at the Tomasulo algorithm. So this is your program. You've got a program which says load, multiply, substitute, divide, and add, right? This is the program which is given. So these are two source operands. And then, this is your destination register. And there are these pipelines. So, here you have got issue, completion, and write result. So completion means finish of execution, but finish of execution and then, comes writing of result. There is a separate pipeline which has got 3 loads, right? So load 1, load 2, load 3. So I mean, this is a really good processor which has got 3 parallel load pipelines. And similarly, there are functional unit is like add functional units, so add 1, add 2, add 3, and 2 multiply units, mult1 and mult2. So add can also do subtract. So if a subtract instruction come, it can go into one of these add units. And similarly, mult unit can also do divide. So if there is a divide instruction, it can go in mult1 or mult2. Okay, so this is your basic thing. So here you would start writing, and let me just, there are example speed is 3 clock cycles will be taken for add and subtract, 10 for multiply, and 40 clock cycles for divide. Now, you may say that, okay, oh, isn't this going against your, what you say is the theory of risk that, one operation in one cycle? Well, as I told you earlier, what happens is if the speed is too fast, if you're running at your processor at 3 gigahertz speed, that means you are getting only 0.33 nanosecond. Then, you break down your ALU operation into 3 parts, right? So your add will take 3 cycles, right? So in one cycle, there will be some intermediate calculation. It will go over here, again, some intermediate calculation, and here the final calculation would come out, right? So to speed up your processor, you have to do this. And so similarly for multiply, you are having 10 such cycles. And for divide, you are having 40 such things. So the reason for this is that, otherwise, if I had not divided this into 3 cycles, this multiply into 10 cycles and divide into 40 cycles, then, everything would be running at the speed of divide thing, because, it is the slowest operation. It is taking 40 cycles. So your overall speed would have been reduced a lot. Okay, so so now let us start looking at the example. Is this readable to you?
Yes, sir.
Okay. Can you still see it?
Yes, sir.
Okay. So here what I have is, first, I will put in the first cycle, I will put in load instruction. So when load instruction goes in here, it will be going into this particular entry. So load 1, I'll be using that up. So busy signal would be going into yes, right? And then, address, so wherever it is, the address would come over here. So that will be there in the force, and issue, you are issuing it in the first cycle. So this is at clock 0, when, this is your static thing, this is a blank slate. Now in clock cycle number 1, the value which you are going to create, the R6 value, is going to be created by this load 6. So whichever one is going next, so which requires R6, and if by that time this value is not created, it would have this number, load 1, into it. So we'll see. So this load 1, the first load instruction has gone into this pipeline. Busy status has gone from no to yes, and the address is 34 plus content of register R2. And it is issued in the first cycle. Okay. Now in the second cycle, you are issuing the second load. And you can do that because, you have got second pipeline. So second load pipeline, the busy status is going to change from no to yes. This is the address. And the value which is going to be generated, which is R2. So that is given by identifier load 2. Now look at the third cycle. The third cycle is the multiply instruction would go into this multiply thing. Its VK is R4, right? So R4 is available, but R2 is yet to be calculated, and it is coming from load 2. So you will put entry under QJ as load 2, right? And in the meantime, load 1 has finished execution. It took 3 cycles. So the third cycle, load 1 is finished. So now value of R6 should be available. Please stop me if you don't have, if you have any problem. This, actually goes on and on. I'm just doing few cycles, and then, you can do it, because, otherwise it would take way too much time. It would take up to 40, 50 cycles to complete the whole problem. So as I said, register names are removed or renamed in reservation station. So as you can see, your R2 is renamed as load 2, right here. So this is basically so that, no confusion is created. R2 is never mentioned until this value will be passed on to this one, and then, it can start using it. So basically this instruction has been issued, but it is waiting for load 2 to finish. It cannot start execution. So here is, you can see it is waiting in the reservation station and not starting execution. So in cycle number 4, the second one has finished, and by the time the first load is now able to write its results. So now the value of R6 is fresh in the register file, and your load 2 has just finished completion. So is it available to it right away? Still no. And in the meantime, the sub instruction has been issued, and sub instruction has gone into this particular pipeline. So operation is subtract, and your VJ, that is R6, is available, but the second one, R2, is still not available, right? Because it has not been written. So these two, as you see, still are blinking in red, because this one has just finished execution. Now in cycle number 5, now these things are available. So this subtract operation can go forward, because the value of this is now available to it, and it can start executing. So now you will see that VJ and VK are available for both. And in the meantime, you have sent divide instruction over here. So it is waiting for R8. Is it R8? Yes, it is waiting for R8 to be finished, which is going to be available from add 1. Just 1 second. Okay, so this is waiting, this divide is waiting, this R0 operand is waiting for this multiply to finish. So that's why it is multiply 1 first pipeline, or first functional unit, is written over here. So you can keep on going, and you can finish the whole thing. It would require some patience on your part, because it is, as I told you, it is a bookkeeping exercise, and you will exactly get the idea that how the bookkeeping is done, when this particular instruction would be issued, when will it be finished, and how you should go about it. So I mean, this would go on for a long time. I have not put in all the steps. I will give this PowerPoint slide to you so that, you can just go and do it. I have only done it till cycle 16, but, you can keep on going because things would stop only when divide instruction is completed, and divide instruction would take 40 cycles, and, a multiply would take 10 cycles. So, it would keep on going and on and on and on. I will not ask you a problem which is this tedious and long. I may ask you a very short problem on this, but, the idea should be clear that, this is how things are done. And if you want to, this is an algorithm. So, if you want to implement this in, say, Verilog or any hardware description language, you can write a program and, you can generate FPGA for this, and, you can have your own processor going in no time. Does anyone have any question?
Sir,
Yes.
sir, in the fourth cycle itself, the second load got its compiled its value R2.
1 second.
So
You are saying in second load? Yes, R2.
So for the multiplication instruction below it, now in fourth cycle itself.
So this is finished at the end of the fourth cycle. So result is to be given in the next cycle.
Oh, okay.
Because, it would take like one cycle to finish execution. So second, third, and fourth. So it takes, we have assumed that load takes 3 cycles. So the end of the third cycle, it would finish. So this is the third cycle, right? The 2, 3, and 4. So fourth, at the t equal to 4, the third cycle would finish for this load. So it will be available in the next cycle for sharing.
Yes, sir. Okay.
So, you can go based on your stamina at how far you want to go. But this idea is very good for understanding. And, this is what is still used in some of the most modern processor. They may be using some, clever things here and there. They might be using fast interconnect. And, how these buses are checked, there is a common data bus. So, all the function units keep an eye, all the reservation stations keep an eye on the common data bus. So as soon as they know that value of R4 is available from function unit 1, it would just bring it and, copy it. So those things, you can do it when you start doing Verilog programming. And, you can write a program for implementing this in hardware. Okay, so that was instruction level parallelism, that, you are changing the order of instructions, or, you are sending them together, you're doing out of order execution. So all those things were instruction level parallelism. Now, you want to go into loop level parallelism, because, in instruction level parallelism, you will say that, in any program that you write, you must have seen that, maybe every 10th instruction or 15th instruction is sort of a conditional statement, right? So there is a conditional statement, means it is branch. So instruction level parallelism, you have got available only 10 or 15 instruction which you can play with. And, can I change this? Can I put this in? Can I put this out? So now, if you want to do something better than that, you go to loop level parallelism. That, can I go across the loop boundary? As soon as you talk about that, going across the loop boundary, you are talking about two things. Either, you are predicting, that means you are speculating that, whether the branch would be taken or not taken. Or you can unroll the loop, means open it up and remove the overhead of terminating condition. So let us look at this simple program that, you have written this program that you are saying the first, okay, let me unroll the loop. So, you are doing this for, 1,000 times you're doing. can you open up the loop twice? You can say, yeah, I can, but I need more registers because otherwise I'll be overwriting. Then I say, okay, probably let's check. I've given you 15 registers to play with. Check whether you can have that. Then I may ask, can you open it up 4 times? Can you open it up 8 times? Can you open it up 16 times? More you have open, better it is. What would go away? Look at this program. Analysis of this program would show, this is, I have written this in ARM assembly language. This is in C language. So in ARM assembly language, you will see, okay, 3 instructions is useful work and 2 instruction is just overhead. Yeah, I'm just checking whether, the loop is to be terminated or not. I'm just, decrementing the pointer by 4 bytes. And then, I'm saying that, whether it's the branch is over or not. So if I run it as is, this program which is given, it will take 7 cycles. That, this load and add, as we know that, there is a dependency, and, this dependency cannot be taken away by whatever amount of, for data forwarding you do, this dependency will not go away. So you say, okay, I will have to stall. You're doing nothing. This is just a loop you're running without scheduling. Then there is add, then there is store, then there is sub, list. And then, after this, you have to have at least one stall to know whether you have to take this branch or not. So basically, there is 7 cycles per iteration. So that means you require 7,000 cycles to finish this. Now, you are doing little smart thing. You are doing static scheduling. That is, you are doing some instruction level parallelism. So you are saying, okay, I'm throwing this instruction and, changing the order. And, I'm putting it over here. And then, I'm taking this instruction out over here. And so, can I do it? But, you would have noticed one thing, that store here was written like this. If I put it after this branch, if not equal, and this sub instruction, then to make this program correct, I will have to do this. Otherwise, my program will not be running properly. So this is the loop with static scheduling. So yeah, you have saved 2 cycles. So instead of now 7,000 cycles, this will take 5,000 cycles. Now you say, okay, can I do something better yet? So then I say, okay, unroll the loop, but do it only as many times as you have registers available. So now you can see I have to use different registers. So I'm using R4 and R0. Here I'm using R8 and R6. I'm using R12 and R10. And here I'm using R16 and R14. So I'm allowed to do only that much loop unroll as there are number of registers available. Otherwise, I will not be able to unroll it. Suppose if I had not done this, and if I had just written these 3 instructions 4 times, then what would happen? You would do this, then you would override this result by a second loop. Again, you would override this result by third loop, so on and so forth. You would not be actually saving anything, and you will get a wrong result or just one result instead of an array. So if you want to unroll this, then you have to also take care of doing it properly. So you use different registers and you use offsets properly so that you get a proper answer. So this is what you would get. You are doing this unrolling, and you are still not saved much. Why you are not saved much in just loop unrolling? Because problem here is still remaining, R0 and R0. So there would be a bubble over here, and then there would be another bubble over here, and so on and so forth. So you have not done much saving. So the best thing to do, and which is being done by your processor, is loop unrolling and scheduling. So what you have done here is you have put all loads together, but you can see here that registers numbers have changed and the offsets have changed. So that means You're allowed to do this, and none of the loads are going to affect each other. Why? Because they are using different registers. So you can, if you have 3 load pipelines together, you can put these 3 loads together. Similarly, all these ads are not going to cause problems to each other. Why? Because they are using different registers. So no problem. And same thing over here. That, store, and, you are doing this, with some proper offset. So you are doing this. So you are doing now 3,500 loops. So you are, on an average, you are using 3.5 cycles per loop, as opposed to 7 cycles, which was done on a totally raw program, which was neither unrolled nor scheduled. So you have done 50% of saving, right? So this is what you would do if you do not have a compiler, or you are writing a program for a small processor, where it is a bare bone thing. Say Cortex M0, where you're given maybe a 1 KB of memory or something, and you have to write a program. You can do a good service to this by writing a program like this, by doing hand optimization, and then you can run this program at least twice as fast as you would be doing in a program which was not loop unrolled, nor which was scheduled. So I think you should go through this. I will send the slides to you. I'll put it in the Google Classroom, and you can take a look at it. You need to look at this carefully. And if another program is given, you should understand what offsets to give. So this is just a program which is fictitious thing, which is not necessarily for ARM, because a number of registers are more there. But if I give you a program like this, and if I ask you that how many times you can unroll for, say, ARM processor with given number of registers, then you have to make sure and be very careful, because there are certain registers which you cannot use. You can use, or you should use, only general purpose register and not overwrite your program counter or your other tool like stack pointer or other things. So in that case, you have to be careful, and you write the number of registers only as whatever you have. Some of you might be more clever, and you can do this. So try to do this program, which is given to you, the first program, and unroll it for an ARM processor, and see how many times you can unroll it. Okay, so that is going to be your homework assignment, and probably you can ask that maybe next Thursday or Thursday after that. But at least I would like you to do it yourself. It would be good for exam. Does anyone have any question?
Sir,
Yes.
sir, till what date will be having classes?
Why are you worried?
Uh,
You want to
because
go somewhere?
no, today morning someone asked that in the algorithms one course that after we'll get some holidays before the exams.
Well, your exam is on 16th, this particular exam. So at least till 6th or 8th of December, we should have classes. I think it depends on you guys, because last 2 classes would be revision. So then, it would be optional for you whether you want to go through revision or not. But I sincerely recommend that to go to the revision or attend the revision lectures, because then, you would get to know what is going to be discussed. And since it is fresh revision, you may get an idea of how the final exam would be like.
Okay, sir. Thank you.
So exam starts from 12th, or what date the exam starts?
13.
13th.
Yes.
So I think it is not very painful if the lectures are there till 8th, right? Okay, up to you guys. But I think last 2 lectures I would like to keep at revision lectures. Okay, any question? Okay, the last one is software pipelining. This is you are taking loops. I mean, I'm not going to discuss this in too much detail. Actually, it is a really interesting compiler issue and hardware issue. And this is done in complicated softwares, but I'm just giving you an idea what is software pipelining. That you have got this iteration 0, iteration 1, iteration 2, 3, 4 of a given loop. What you are doing is this. You are taking different instructions from different iteration and then putting them together. So this would be like total optimization, that you are using load from iteration 3, you are using add from iteration 2, and you are using store from iteration 1, and then making a one program like that, where the first instruction is from third iteration, second instruction is from second iteration, and third instruction is from first iteration. And then I mean, you require a lot of imagination to understand this, that how, whether they would be causing any problem or not. But this will be the most optimized thing of software pipelining. I'm not going to go into any detail into this, nor I would ask you any questions about this in exam, but I would just like you to know that there is something like this in software pipelining. Here, what you are doing, that from the same one, you are just putting things together. Whereas here, you are taking instructions from different loops. So first instruction from this iteration, second instruction from second iteration, and third instruction from third instruction, and putting them one after the other. So that is sort of, I mean, it is giving you time for one particular instruction is waiting from previous data. That instruction would come later on, so that there is no problem between different instructions. So that is a kind of a software pipelining, and probably you don't require as many registers as you are requiring over here. But this is, I think, best to be done by very experienced programmer or a good compiler. Okay, so this is a final thing is stress scheduling, and I told you that this is a huge speculation where you speculate over all branches, and you make one inline program without any conditional statement, and you go through it. I mean, this works very well if your speculation is successful. Otherwise, there will be a price to pay for it, misprediction. So as I told you, prediction is a great idea as long as you don't mispredict too much. If you start mispredicting it, then your hardware will stop prediction, and it will stop using your sophisticated predictor, and then it will say, okay, these predictors are not working. It is giving me wrong answer, so I'm going down to most basic predictor, which is sort of like static predictor, that forward branches not taken, backward branches taken. Okay, so we stop at this point. We are done with superscalar processor. In superscalar processor, if I want to say in very few words what issues were there beyond what we have seen in inline processor, then the only thing for that was that you have multiple pipelines, and the additional issue was put in at the issue stage, where you have to worry about raw hazard for the instructions which are going in. You can also have war hazard, which you will put over here, and finally your wow hazard will be taken care of when you do write back, and you will allow write back only in order, so that you don't have wow hazard. So that is how the additional issue of superscalar processor with multiple parallel execution unit is there, and this is the additional issue apart from all other issues you would have in inline processor. Okay, any question? Okay. So I will stop over here. And if you don't have any question, then I'll stop.